All right, welcome back, everyone. If you're gearing up for your communication engineering course, EE3207, you are in exactly the right place. Today, we're tackling the ultimate villain of communication systems, noise. Specifically, we're going to look at how different continuous wave, or CW, modulation systems actually fight back against it. Whether we're talking about transmitting voice over classic AM radio or streaming high-fidelity audio over FM, noise is that great equalizer, right? It's always there. So our main goal in this explainer is to figure out exactly how noise infiltrates our systems, and more importantly, use some hard math to prove which modulation techniques actually survive the best.
So here's our game plan for today. We'll start by building a baseline with the noisy receiver model and AWGN. From there, we'll benchmark three specific systems: the DSB-SC baseline, then we'll hit the AM threshold effect, dive into the FM noise advantage, and finally wrap up with the FM threshold crash. Let's get right into it.
Section 1, the noisy receiver model and AWGN. Okay, so our primary adversary in communication engineering is AWGN. Now, let's break that down real quick. It's additive simply because it, adds itself directly to our pristine transmitted signal. It's white because just like white light contains all the colors of the spectrum, this noise contains all frequencies. It has a constant power spectral density of N0/2 across the entire spectrum. And it's Gaussian because its amplitude perfectly follows a normal bell curve distribution. Now, here's the kicker. Once this wideband front-end noise passes through our receiver's bandpass filter, it transforms into narrowband noise. We express this mathematically in a canonical form, essentially splitting it into two distinct parts: the in-phase component, NI of t, and the quadrature component, NQ of t. And honestly, really understanding this split, that's absolutely crucial for analyzing everything else we're going to talk about today. Moving on, let's think about our standard testing ground, the linear noisy receiver model. Considering the input, we've got our modulated signal, S of t, and our additive noise, W of t, joining together right at the summing junction. Together, this combo passes through a bandpass filter. Now, this filter is an ideal one, totally centered right at the carrier frequency, and its entire job in life is to restrict the noise to only the transmission bandwidth. The output of this filter, X of t, which is now our signal plus that narrowband noise we just talked about, is what finally hits the demodulator so we can recover the actual output signal. Now, if we want to objectively compare the performance of these demodulators, we really have to distinguish between three very specific signal-to-noise ratios, or SNRs. First up is the input SNR, which is measured right before the demodulator. Think of it as a preliminary measure. Second is the output SNR, measured at the receiver's output. This one is our primary measure of fidelity. It literally tells us how clear the actual message is to the user. And finally, we have the channel SNR. This is our vital reference benchmark. It represents what the SNR would be if we just transmitted the baseband signal directly over the channel, zero modulation involved. It essentially normalizes our receiver performance so we can fairly compare AM, DSB-SC, and FM on a totally level playing field.
So that brings us to this absolutely crucial formula, the figure of merit. It's simply the output SNR divided by the channel SNR. You can basically think of this as a recurring scorecard for today's explainer. It's how we grade every single modulation scheme. Look at it this way. If the figure of merit is exactly 1, the modulation performs exactly as well as a direct baseband transmission. If it's less than 1, well, the modulation scheme is actually hurting our noise performance. But if it's greater than 1, that means the modulation scheme is actively fighting back and improving our signal clarity against the noise.
Section 2, DSB-SC, the perfect baseline. Let's talk about double-sideband suppressed carrier, or DSB-SC. The real secret sauce here is the product modulator sitting inside the coherent detector. Unlike simpler receivers, this one actually generates a local carrier signal, cosine of 2 pi FCT, and multiplies it directly with the incoming noisy signal. Now, remember those in-phase and quadrature noise components we talked about a minute ago? Because the local oscillator is perfectly in sync with the incoming carrier, it perfectly aligns with the in-phase noise, but, and this is huge, it's exactly 90 degrees out of phase with the quadrature noise. So when you multiply them together, that quadrature noise component is just mathematically rejected. Poof, gone. The noise simply appears additively with the message, completely independent of the input SNR. And because it perfectly rejects exactly half the noise, that pesky quadrature component, the output SNR ends up being exactly equal to the channel SNR, which means the DSB-SC figure of merit is exactly 1. Bam! This establishes our ideal linear baseline. There is absolutely no noise penalty for using DSB-SC compared to a direct baseband transmission. For linear modulation, this is literally the gold standard. Section 3, AM and the threshold effect. But what happens when we replace that fancy coherent detection with a simple, nonlinear AM envelope detector? Well, we start facing some major flaws. While these detectors are incredibly cheap to build, which is exactly why AM radios were historically everywhere, they have two fundamental issues. First off, standard AM wastes a massive amount of transmission power simply broadcasting the carrier wave itself, which actually contains zero message data. Because of this wasted power, even under absolutely perfect conditions, its figure of merit is fundamentally capped at less than 1/3. But more importantly, the envelope detector is nonlinear, and that fundamentally alters how noise impacts the system whenever the signal strength gets low.
And this brings us to a really critical failure mode in communication engineering known as the AM threshold effect. This is a unique, pretty harsh penalty of using nonlinear detectors. See, as long as your signal is strong, the detector works totally fine. But the very second the carrier-to-noise ratio drops below a certain threshold, the whole system just completely breaks down. Suddenly, the noise envelope, RFT, strictly dominates the output. Your message isn't just a bit fuzzy, it gets multiplied by totally random noise phase variations. The end result? A complete and total loss of your information. It's just gone.
Thinking about this as a phasor representation, we can see exactly how this disaster unfolds. The vector representing the carrier signal is trying its best to dictate the overall amplitude. But when that carrier vector shrinks down due to a weak signal, and the noise vectors Ni and Nq become relatively large, the noise envelope completely takes over the resultant vector y of t. And the envelope detector, it just blindly follows the length of that resultant vector. So instead of tracking the smooth, intended amplitude variations of your message, it tracks the chaotic, swirling, random noise vectors. It basically mutilates your message into pure, unadulterated static. Moving on to Section 4, FM, the noise advantage. All right, let's see how FM outsmarts all of this. Notice the block right before the discriminator, the limiter. This thing is the absolute secret weapon. Remember, noise primarily messes with the amplitude of a signal, while the limiter aggressively shaves off all amplitude variations. It completely clips the top and bottom of the wave, effectively erasing the space where the AM noise actually lives. It then passes this constant amplitude signal straight to the discriminator, which extracts the message based solely on frequency changes. Alongside this, we're starting with the flat, rectangular spectrum of narrowband noise, right before the discriminator does its work. Now here is where the math gets really, really elegant. The FM discriminator works by taking the derivative of the instantaneous phase to figure out the frequency. In the frequency domain, taking a derivative means you multiply by the frequency f. So when we're dealing with power spectral density, we have to square that. This means we are mathematically multiplying the flat noise spectrum by f squared. What does that do? It results in this famous parabolic noise effect. The noise power at the output of an FM demodulator isn't flat anymore. It increases parabolically as you move out to higher frequencies. And honestly, here is the absolute magic of wideband FM. Just think about the figure of merit equation. It equals 3/2 times beta squared. Beta is our modulation index. This means the figure of merit isn't locked at a maximum of 1 like DSB-SC or stuck below 1/3 like AM. It scales up heavily by increasing the modulation index, which basically means intentionally using a much wider transmission bandwidth. You actually square the improvement in your output SNR. This is the fundamental noise bandwidth trade-off in action. We are actively sacrificing our bandwidth to achieve an incredible, highly resilient signal-to-noise ratio. Which brings us to our final part, Section 5, the FM threshold crash. Okay, so there's a catch. Similar to the AM envelope detector, the FM discriminator is a non-linear device, which means, you guessed it, it also suffers from a threshold effect. But the FM threshold is so much more violent. While an AM signal might slowly, gradually fade into static, an FM signal crashes abruptly when the carrier-to-noise ratio drops too low. What's happening under the hood is that intense noise peaks are causing the instantaneous phase to suddenly wrap around by 2π. The discriminator reads this sudden, violent phase jump as an extreme spike in frequency. And how does that output? As harsh, loud, highly audible clicks or pops that completely destroy whatever you're listening to. But hey, engineers are problem solvers, right? To fix this abrupt crashing issue, they developed the FMFB, or FM feedback receiver.
It's brilliant. It takes a portion of the output signal and feeds it right back into a voltage-controlled oscillator, or VCO, which acts as a dynamic local mixer. This feedback loop dynamically compresses the frequency deviation of the incoming signal, effectively reducing the modulation index that the discriminator actually sees. By doing this, it keeps the discriminator safely operating in its linear region, even at much lower signal strengths. It successfully extends the threshold and delays that catastrophic crash.
So as you review these linear and nonlinear models to prep for your EE3207 exams, I really want to leave you with a question to chew on. Is the massive bandwidth cost of wideband FM always worth the SNR improvement in modern engineering? When spectrum is so incredibly limited today, when is it truly worth trading that precious bandwidth for perfect clarity? I mean, think about how these foundational noise bandwidth trade-offs impact the design of the digital cellular networks you literally use every single day. Something to think about. Thanks for joining me on this explainer. Study hard, and I will catch you in the next one.